Welcome back, guys. We're going to pick up right where we left off a minute ago. We are looking at this gas cycle and trying to examine the heat exchange. So I want to talk to you guys about a new formula that we haven't done before and doesn't actually appear on your formula sheet. But is probably the easiest formula that we have for things like this. It is the formula for the internal energy of a gas. So let's just draw a line. I'm going to separate it in two columns. So, because I need to talk separately about monatomic gases, gases that have only one molecule, or one atom, and diatomic gases, gases that have molecules made of two. So, examples of monatomic gases would be like mostly the noble gases, helium, neon, argon, xenon, things like that, because they don't like to bond. And diatomic gases are going to be oxygen, that's an M. Oxygen, nitrogen, hydrogen, things like that. So most gases are really diatomic gases, but a lot of times they like to ask you questions about monatomic gases because it makes it a little bit easier, I think. So monatomic gases are just a ball. So they have three ways they can move, or 3 degrees of freedom. Because it can go up, down, left, right, basically. It can go this way, that's 1 degree, forward or backward this way. It can go this way, that's another degree, or it can go this way, that's another degree. That's about all it can do. So forward, sideways, up, I don't know. And you can go negative any of those directions. Now, a diatomic gas has 5 degrees of freedom. So it can go, same ones, it can still go up, sideways, forward. But it can also have, it has 2 more. Because if it's a diatomic gas, it's shaped like a peanut, right? So it's going to be kind of 2 of them like this. So you can imagine it can spin this way. Will be very different. Well, you can have energy there. Or it can spin the other way, right? So it can spin, I don't know, out of the page. Or some combination of them. I'm trying to figure out how to draw this. Kind of like that, I guess. So then 2 axes of spin. So that's 5 degrees of freedom. So the formula for internal energy that we can use is going to be the number of degrees of freedom. So on this side, it's going to be 3 divided by 2 times number of moles times, don't use, I think, yeah, this is supposed to be an R, not a K. I'm starting to write a K, but this is a different version, times the temperature. So R is the universal gas constant, T is temperature, N is moles. And for diatomic gases, so we'll say mon down here, and di. Over here, you've number of degrees of freedom, same thing, divided by 2, times N, times RT. And that's, those are the whole formulas. So this is degrees of freedom on top, times 1/2 nRT. And that gets you the internal energy. So what does this do for us in this case? Well, I can easily calculate the work done in this portion, right? So if I want to calculate, and I can calculate the change in internal energy pretty easily using those formulas. And so then I can just do subtraction and figure out the heat exchange. So that's all I'm going to do. I'm not going to do this MC delta T thing again because I don't want to. Also, I can use this same method to do this branch because, well, I can calculate the area under this curve and get the work done, and I can use the change in temperature to find the heat exchange. So I'm going to go ahead and pause the video. I'm going to find the temperature at C, because I haven't done that yet. And then, well, I'll get right back to you, and we'll have a talk a little briefly, and we'll do some more math. So if we calculate the temperature at point C, we can see that's 1083 Kelvin. Now, I apologize for picking numbers that are a little bit unrealistic. I think it's better than before, what I'm doing now, but I'm just kind of making these numbers up on the spot for the problem. So they're not always going to correlate to reality the best. I don't really have time to do these problems ahead and plan them ahead for exact numbers and make it come out perfect to reality. Anyways, I'm going to pause it now, and I'm going to find the internal energy at both B and C, and we will talk about how much heat is then done or exchanged. So we find the internal energy is going to be 250.04 joules, which any reasonable person will round to 250, especially for an answer. So now I'm going to do it one more time to find the internal energy at point C. So the internal energy at point C is going to be 748.24 joules. And so how do I figure out the heat exchange then? Well, I want to also figure out the work, because I know that the change in internal energy is Q plus W. So heat flowing in plus work done on the gas, right? So I am going to then, so I know this is the internal energy here is this, so I can figure out the difference, right? So I'm just going to round it and say delta UBC is going to be 500, just ballpark. And I can say the work done from B to C is going to be pressure times the change in volume from B to C, or pressure times final VC minus VB. And I'm going to pause it, and I'll get back with an answer. So just plugging in numbers, we find that the work done is 200 joules. This is the work done by the gas, I guess, right? Because the gas is losing this much work. So I guess I'm supposed to actually have this formula with a minus sign here, is what I'm supposed to do. So this is going to be minus 200 joules, because that's work done on the gas. Okay, so that means that if I have done, if my internal energy has increased by 500 joules, but the gas has done 200 joules of work and lost that much energy, how much heat have I gained? Well, it's quite simple. So this has gone up 500 joules, and this is going to be Q minus 200 joules. That means Q, the exchange of heat, is 700. Oh, you can't see that one. 700 joules. And that is going to be heat flowing into the gas. And that's, let's say, BC, just to know where that's happening. All right, sounds good. I'm going to call this one quits, and I will see you in the next one. Make good choices, guys. Stay safe out there.